So a couple of key examples for us to go through then. So we have lines 1 and 2 in Cartesian equation form, and part A asks us to show that a particular point lies on both L1 and L2. So it should be possible then to substitute x equals 3, y equals 3, and z equals 7 into the two equations we have, so the equation for line 1 and the equation for line 2, and still have those holding completely consistently. So for line 1 then, 3 minus 6 over minus 1 is 3, which I'm hoping is the same as 3 plus 3 over 2, which it is, which should also be the same as 7 plus 2, which is 9 over 3. So therefore, A lies on L1. And let's just show that, so you should have a conclusion in there. For line 2, 3 plus 5 over 2 is 4, which should be equal to 3 minus 15, which is minus 12 over minus 3, so that's fine, and 7 minus 3 over 1. Therefore, A lies on L2. If a point lies on both lines, that means it must be where they intersect. So point A is the point of intersection for line 1 and line 2. We now need to find the size of the acute angle between the lines at A. So of course we know the formula for the angle of divergence. So they're going away from each other, and here's our point A, 3, 3, 7. And of course our lines, their sort of orientation are dictated by the direction vector. And the direction vector is on the base of our equations of the straight line. So it is these numbers here, the minus 1, the 2, the 3, the 2, the minus 3, and the 1. So the direction vector of line 1 is minus 1, 2, 3. And the direction vector of line 2 is 2, minus 3, 1. And so these are the two vectors that we will use to find our acute angle. So the magnitude of vector 1 is minus 1 squared, add 2 squared, add 3 squared. Of course, you can do Pythagoras in 3D. So 1 plus 4 plus 9, which is the square root of 14. And that means that the magnitude of D2 is the same because it's the same numbers. So we now also need to do D1 dot D2, find the dot product between them. Minus 1 times 2 plus 2 times minus 3 plus 3 times 1, which is minus 2 minus 6 plus 3. Minus 5, I believe. So our angle then, cos theta is our angle of divergence, of course, is minus 5 over square root of 14, square root of 14. Grabbing a calculator, plugging all of that in, we get that our angle is 110.9 degrees. But we were asked for the acute angle. So we're actually being asked for this one here. We're not even being asked for the angle of divergence. So alpha then is 180 minus 110.9, and so alpha is 69.1 degrees. The second key example is this one. And later down the line, you will be taught a different technique that does this far, far, far quicker. But I think it's really important to see the sort of mechanics behind some of these more streamlined processes. So we're going to give this a go. We want to find a vector which is perpendicular to both vector A and the vector B. Right, so I don't like ij's and k's. I think they get quite messy. So I'm going to rewrite my vectors in column vector form, just so I can play around with them a little bit easier. General rule of thumb, though, if you are presenting something in I, J's and K's, make sure your answer is back in I's, J's and K's. Okay, so we want a vector. Let's call this vector x, y, z, because we don't know anything about it yet. But it has to be normal to both of, has to be a normal to both of them, i.e. it's perpendicular to both of them. So that means that a dot n is 0, and also b dot n is 0, because we know that the dot product equaling 0 means that it's perpendicular. So let's actually go ahead and do that. I appreciate we're going to end up with equations with unknowns in them, but we can be quite clever about those when we get there. So pop our vectors in. So we end up with minus 2x plus 5y minus 4z equals 0. And if we use b, we end up with 4x minus 8y plus 5z equals 0. Now, I have only 2 equations, but I have 3 unknowns. Luckily with vectors, I can create proportional answers and then scale to make things whole numbers, which is really nice. So we're going to look for a proportionally correct solution first. And the way we're going to do that is we are going to set one of our variables, x, y, and z, to a non-zero number. So I'm going to set z equal to 1. And we'll explain why this works in a second. So if I do that, I'm going to get the equations minus 2x plus 5y minus 4 equals 0, and 4x minus 8y plus 5 equals 0. And now these are 2 simultaneous equations that I can solve. I'm not going to spend any time actually solving these equations. Hopefully you can either by, you could do elimination here if you wanted to, or by using a calculator or by using substitution. I mean, there's 1,000 different ways you could do this. You should end up with x equaling 7 over 4 and y equaling 3 over 2. Don't forget, we already set z equal to 1. Now, it was non-zero. That was really important because I don't want to remove z. I want to assume that z has a value and find out what x and y are proportionally compared to it. So my vector then is ending up being 7 over 4i plus 3 over 2j plus k, 1k. And that would be my vector n, the one that is perpendicular to both of them. Now, we know, of course, that we can multiply vectors by a scalar, and they are still the same vector. So I can actually multiply this vector by 4 to get rid of the fractions on all of these terms, and that would still be a vector which is perpendicular to both a and b, because it's a scalar multiple, it's parallel to the vector I found already. So I can actually say n is 7i plus 3j plus 4k. And that will be the answer that I leave for my examiner there. So what we've done there is by making z like a sort of unit measure, we have found how much x and y would change in relation to z changing by 1 unit. And that has created a vector which I can then scale up. Now, this really only works for vectors because we know that multiples of the same vectors are still in the same direction. So nearly always doing this will find us a sort of scaled down vector which still fits our conditions, and then we can scale it up by multiplying by a number, and it still solves our problem. So it's a really nice way of solving these sorts of problems for vectors.